Welcome to the module Understanding Advanced Contacts. In this module, you will analyze a closing and latching operation of the latching mechanism. Along with that, you will get familiar with the definition of solid bodies contact as well as their limitations and uses in SolidWorks Motion. To better understand this, you will create solid bodies contact and resolve the solver errors. You will also learn how to determine the closing force required to close the latch. This module is split into two parts. In Part 1, you will learn how to define the contacts. You will also learn about using expressions to prescribe the magnitude of forces and motors. In Part 2, you will analyze some causes of an incorrect solution or a contact solution failure and use alternative numerical integrators. This module is divided into several topics. Click the topic titles in the list for a brief overview of each topic. An over-center latch is used to hold the carriage parts against a spring. In this module, we will analyze the latching mechanism and determine the contact force generated on the spring lever and keeper as the latch closes and the force needed to close the latch. Geometrical or mechanical constraints to an assembly can be added in SolidWorks Motion using the mate command. An alternative approach to add a constraint is to add a motor. For example, you can add a coincident constraint between two parts using coincident mate, whereas you can have the same constraint by adding a motor between the same parts, setting the motion type to distance, and entering 0 mm in the displacement field. One reason for using a motor instead of a mate is that it does not introduce additional constraints to the motion model. It also helps to reduce the number of redundant constraints. Redundant constraints are explained in greater detail in Module 10, Understanding Redundancies. Let's see how to create a motion study and fix motion using a motor. Click Show Me to launch a demonstration video. The full latch mechanism assembly file has been opened for you. The assembly has several mates. However, not all components have enough mates to allow the parts to move based on the mechanical motion of the final assembly. The carriage part is concentric to the center spindle, but can rotate through the side spindles. Three components of the latch knurled pin, spring, and series lever are not restrained laterally. Verify that the document units are set to millimeters, grams, seconds. Right-click Motion Study 1, and then click Rename. Enter Latch Forces as the new name for the motion study. Ensure that the type of study is set to Motion Analysis. Click Mate. Now, to add a coincident mate between the front planes of the base and series lever, expand Base. And click Front. Next, to select the front plane of series lever, expand Series lever. And click Front. We can see that coincident mate is automatically selected. Click OK. This is a local mate, which means the mate is added in SolidWorks Motion Manager only. We could add another mate to restrict the motion of J-spring, but we will practice an alternative approach to constrain the motion of free parts. Click Motor. Since we need to restrict linear movement, we will select Linear Motor. Click the face of J-spring. The direction of the arrow does not matter. Set the motion type to distance. For displacement, enter 0 mm. Retain the default value for the start time. For end time, enter 3.50 seconds. the simulation will run for 3.5 seconds, so the motor will restrict the J-spring from moving during the entire simulation. This motor will prevent any lateral movement, but will not constrain the latch from moving as it should. The effect of this motor is similar to that of a mate, but acts without mate redundancies, the subject of Module 10. Click OK. Now, we will restrict the rotary motion of the carriage by adding a motor. Click Motor. Since we want to restrict rotary movement, we will ensure that motor type is set to rotary motor. To attach the motor to the edge, click the edge of the carriage. Click the Motion drop-down arrow and click Distance. For displacement, enter 0 degree. Retain the default value for the start time. For end time, enter 3.50 seconds. The simulation will run for 3.5 seconds, so the motor will stop the carriage from rotating during the entire simulation. Click OK. Note that the motion study is created and the linear motion of J-spring and rotary motion of carriage are fixed using motors. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about creating a motion study and fixing motion using a motor. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed this simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. SolidWorks Motion allows us to set the inputs for a motor in a number of ways. We have used constant speed, distance, and data points in most of the modules so far. However, expression, oscillating, and segments are also available. Expression allows you to define a profile that dictates the motion of a motor with the help of various mathematical functions. Functional expressions are used to define the magnitudes of inputs for motors and forces. Click the arrowheads along each edge of the content frame to move to the next slide. Functions can depend on time or other system states, such as displacement, velocity, and reaction forces. Functions can be created using any valid combination of simple constants, operators, parameters, and available supported solver functions such as step and harmonic, SHF. There are 6 types of force functions that can be used to define the force, such as constant, step, harmonic, segments, data points, and expression. Constant sets a constant value of a force. Step defines a step by an initial value, start time, final value, and final time. Harmonic defines the value by amplitude, frequency, average, and phase shift. Segments defines the value by combining segments of the most commonly used functions, such as linear, polynomial, half sine, and others. Data points takes the values from a table of data points and interpolates a spline between the data points. Expression defines the value using a formula. A step function prescribes the given quantity between 2 values with a smooth transition. Before and after the transition, magnitude of the given quantity is constant. For example, consider the step function for displacement where d0 equals initial value of displacement, d1 equals final value of displacement, t0 equals start step time, and t1 equals final step time. Let's see how to define a motor using functional expressions. Click Show Me to launch a demonstration video. We will create a motor that will flip the latch up and then flip it back down to lock it in place. The motor will be driven by a functional expression with 2 step functions, one to flip the latch up and the other to flip the latch back down. Click Motor. Ensure that rotary motor is selected as the motor type. For the motor location field, click Axis 1 of the series lever. This motor will simulate the action of the hand operating the series lever to open and close the latch. Click the Motion drop-down arrow and click Expression. The Function Builder window appears. In Function Builder, make sure Expression is selected. Ensure that Mathematical Functions is selected as the input type. Double-click on Step function to insert it. We now need to add parameters in the step function. Modify the added functional expression to read step time 0, 0, 1, 90. This will have the effect of rotating the latch from 0 to 90 degrees over time, 0 to 1 seconds. The expression as it's currently written will lift the latch up. We will now add to the expression and bring the latch back down. To complete the expression to its final form, add the same step mathematical function again. Double-click to insert it. Modify the newly added functional expression to read step time 1.503 minus 90. This will bring the latch down 90 degrees from 1.5 to 3 seconds. The Function Builder graph window will update the plots for displacement, velocity, acceleration, and jerk automatically. Click OK to complete the definition of the expression and close Function Builder. Click OK to complete the definition of the motor feature. We now need to define a spring with a damper, which generates tension to keep the latch pulled tight. Click Spring. Linear spring is selected by default. Enter 10 newtons per millimeter as the spring constant value. For spring location, click the edge of the carriage, and then click the edge of the main body. Notice that the free length of the spring is automatically populated into the free length field. Retain free length at its default value. To add a damper, click Damper. Ensure that the damper type is set to linear. For damping constant, enter 0.10 newtons per millimeter per second. Click OK. Note that the motor is defined using functional expressions. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about defining a motor using functional expressions. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. Contacts are defined between two or more bodies or two curves. During the definition of the contact between solid bodies, whatever feature we pick on the parts, the corresponding body will be selected and used for the contact analysis. As the software starts solving the contact analyses, the bounding boxes of the parts are calculated at each frame. As soon as the boxes interfere, a finer interference calculation is done between the two bodies. An impact force is computed from the center of gravity of the interference volume and then applied to both bodies. Click the arrowhead along the content frame to move on to the next slide. To understand the contact treatment in SolidWorks Motion, we first need to reiterate the original assumption of the modulus. All parts participating in the motion simulation are rigid, but in the real world, there is nothing which is absolutely rigid. We solve the analysis with the assumption that all bodies participating in the motion study are rigid in nature, which results in elastoplastic deformations with severe localized strains and significant changes in the geometry of the contact region. This shows that approximations are therefore necessary. SolidWorks Motion allows for the specification of the contact parameters using two distinct approaches, such as the Poisson model and impact force model. Poisson model, also known as restitution coefficient, is based on the utilization of the restitution coefficient E, which is defined in the formula shown on the screen, where V1 and V2 are the velocities of the spheres before the impact, and V1' and V2' are the velocities after the impact. The bounding values of this coefficient are 0 to 1, where 1 indicates perfectly elastic impact where no energy is lost, while 0 indicates perfectly plastic impact where the parts adhere after the impact and maximum possible energy is lost. The restitution coefficient is geometry dependent. It does not require specification of the damping coefficient and does account correctly for the energy dissipation. Hence, it is recommended if the energy dissipation is of great importance in the simulation. Also, determining the Poisson model parameters and the restitution coefficient is more straightforward than determining the parameters in the impact force model. This model is not suitable for the persistent impacts, that is, the impacts where contact is developed for a prolonged period of time. Impact properties or impact force model in SolidWorks simulation allows the calculation of the contact force using the expression shown on screen, where K represents the stiffness of the contact, E is the elastic force exponent, and C is the damping coefficient. To correctly determine the stiffness, a possible solution is to model the configuration of the contact in SolidWorks simulation finite element software, apply any force in the direction of the impact, and solve for the displacements. Stiffness can then be readily obtained from the force magnitude and the resulting displacements. A figure demonstrates the impact configuration of two spheres meshed in SolidWorks simulation software. In many instances, the elastic solution can be found in various engineering publications. It is apparent that the computation of the contact stiffness K can be a daunting task, and simplifications have to be introduced. The exponent parameter E controls the degree of the nonlinearity in the elastic force. If E equals 1, then it constitutes a linear elastic force. Damping coefficient, which is nothing but a measure of the capacity to dissipate energy, increases from 0 to its maximum value. Damping coefficient is 0 at the start of impact. It is maximum when a certain specified deformation is achieved. A typical value for the maximum damping coefficient, Cmax, is 0.1% to 1% of the contact stiffness, K. Penetration is equal to deformation at the end of the impact. For any deformation larger than the penetration d, the damping coefficient is constant and equal to Cmax. Let's see how to define contact between the latch and latch keeper. Click Show Me to launch a demonstration video. Let's define the solid body's contact among the latch arm, latch lever, and latch keeper. Click Contact. Under Contact Type, ensure that Solid Bodies is selected. Click the arm portion of the J-spring. Click the latch lever. Click the latch keeper. Ensure that material type is set to steel, dry for all the selected bodies. Retain the friction at its default values. Here, we are trying to make the impact more realistic by simulating the collision of two hard metals. The elastic properties of the contact are only approximate. More realistic values would be required for a contact region solution. Click OK. Now we will apply gravity. Click Gravity. To define gravity in the negative x direction, click X. Click OK. Click Motion Study Properties. Verify that frames per second is set at the default value of 25. Scroll down. Contacts are calculated in SolidWorks Motion by tessellating the faces of the contacting bodies. The tessellated surfaces are then used in the contact analysis. The size of the tessellations are determined by the 3D contact resolution slider bar. A low resolution means fewer but larger tessellated surfaces, while a high resolution will result in a higher number of small tessellated surfaces. A high-resolution contact will lead to a more accurate contact resolution but a larger solve time. A low-resolution contact will have the opposite characteristics. Moving forward, We will attempt to solve this simulation using several contact settings. In Motion Study Properties, drag the 3D contact resolution slider all the way to the left and set it to its lowest resolution setting. Keep the rest of the settings at their default and click OK. Set the time bar key to 3.5 seconds. Click Calculate. The solver may fail prematurely with several messages in the error window. If the solver goes till 3.5, the contact solution would not be very accurate. There can be a few reasons for such behavior. The first reason is the time step of the integrator solver is too large, in which case the contact is not even detected. The second reason is the accuracy setting is too high or too low. The third reason is the geometrical description of contact is insufficient. In the present case, the geometrical description of contact is causing the incorrect solution. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about defining contact between the latch and latch keeper. Click Try It to launch the simulation and go through the steps on your own. Congratulations! You have successfully completed this simulation. Click Next to continue. SolidWorks Motion treats the geometries of the contacting solid bodies in two distinct ways, which are tessellated geometry and precise geometry. In the case of tessellated geometry, the surfaces of the contacting bodies are meshed with the triangular elements to simplify the description. The density of the mesh, that is, the contact geometry resolution, is controlled with 3D contact resolution in the study properties. Because this description is very efficient, yet typically sufficient to obtain accurate solutions, tessellated geometry is the default choice. Very coarse description may result in inaccurate solutions or may even fail to develop the contacts. This is also the cause of the solution failure in the present case. If the tessellated geometry description is not sufficient, then precise contact option can be used instead. While this is the most accurate description, it can be computationally expensive and should be used with caution. Use this option if your contacting bodies feature complex or point-like geometries. Examples of the tessellated geometry at two resolution levels and the precise geometry are as shown on screen. Let's see how to improve the accuracy of the tessellated data. Click Demonstration to see how this is done. click Motion Study Properties. Drag the slider to set 3D Contact Resolution to High. Click OK. Click Calculate. As an approximate representation of the contact is being used, the solution may fail prematurely due to a lack of convergence. The simulation will fail and display the failure message. After reviewing the message, we can find that there are some possible problems. The first possible problem is that the solver fails to achieve the specified accuracy. We will try decreasing the accuracy of the solution. While calculating the study, the parts are moved too quickly, which suggests that the Jacobian should be evaluated more often. Since the Jacobian setting is already at its maximum value, we will achieve this by also reducing the maximum integrator step size in the advanced options of the motion study properties. The point where the solution fails is when the latch reaches the over-center point because of instability in the solution. That brings us to the end of this demonstration. Click Next to continue. Here's a question to check your understanding of what has been covered so far. You've reached the end of the module, Understanding Advanced Contacts, Part 1. Here are the key takeaways from the module. Click each tab to learn more.